Okay, so today I want to, the goal today is to study the limits of stretched lines in Teichmüller space union the Thurston boundary. I will recall a few things which I said several weeks ago on Thurston's boundary, because they asked me to. They want the recording to be self-contained. I will recall a little bit, and so this is the goal today, and the general goal, in fact, the general goal of all these lectures is to present Thurston's theory of the metric structure on Teichmüller space, and to extend and some other results. Results which are not in Thurston's paper. So this is the general goal. This is the goal today. So I want to. So as you saw, I want to insist on these constructions and analysis of ideal triangles. As you will see, there's a main lemma here in the study of limits of stretched lines, which is a geometric lemma, which is something. Everything goes on in an ideal triangle. So this is the basic thing, and this makes it very simple. In fact, these are very simple ideas from hyperbolic geometry, and the fact that they are that everything is concerned this ideal triangle means that they cannot be extended to Euclidean or to spherical or to other kinds of geometries, because we have no ideal triangles. Okay, so let me, what do I write here? What did I write here? Okay, so let's start with an ideal triangle. Ideal triangle. So we saw that with an ideal triangle we can construct a surface by gluing several ideal triangles. We can construct a surface, hyperbolic surface. This is an easy way to construct a surface by gluing ideal triangle. We saw that we can also construct a surface with boundary, which is a pair of pants, by gluing two ideal triangles. They will spiral along the boundary components, and also we can construct a closed surface, closed hyperbolic surface by gluing. Here I'm gluing two of these ideal triangles with these. I'm gluing two of these pairs of pants. So we know how to construct a closed surface by gluing ideal triangles. by gluing 4 ideal triangles. Okay, so now the next thing is also something we saw, is that associated to an ideal triangle, there's a canonical foliation. Ideal triangle, there's a canonical foliation which we call the horocyclic foliation. And horocyclic foliations, as soon as we glue ideal triangles, they exist here, they exist here, they exist there. We have the horocyclic foliations provide a foliation on our surface. Let me mention here that there's here a non-foliated region here, small non-foliated region, but I can make it. I will say later on what we do with this non-foliated region. So it's a foliation, except that there's a region of the surface bounded by 3 horocycles which are not foliated, but this is okay. We'll deal with this. And then we saw also that since you are dealing with hyperbolic surfaces, while complete hyperbolic surfaces, geodesically complete, and okay, I want to say a finite area, but this is not important now, because what we are doing is just gluing ideal triangles, so a finite number of ideal triangles, so the result will be a finite area. We don't need to care about this finite area. And then we saw that there's a condition for this. There's a condition for this, is that this horocyclic foliation along, while at every puncture is a foliation by closed leaves. So when we glue a finite number of ideal triangles, we take their horocyclic foliations, we get a foliation on the hyperbolic surface. The surface, in order to be geodesically complete, we have to have this condition. This is what we saw last week. Here, for surfaces with boundary, there is no such condition. In fact, this condition does not make sense here anyhow, because we don't have. I mean, we don't have punctures. The ideal triangles are spiraling along these curves, and we don't see the vertices of the ideal triangles. Okay. Okay. So this is something. We know now. So here, when the Thurston boundary, let me recall something we said long before. This is the Thurston boundary. This is called PMF, and this is equivalence classes of measured foliations. On the surface, which I call S. I will talk more about this, but here we have this space of measured foliations, and right from here, let me say or recall that the horocyclic foliation, whether it is the horocyclic foliation of an individual ideal triangle or a horocyclic foliation obtained there by gluing ideal triangles, or obtained here, This is in fact a measured foliation. That is, it has an invariant transverse measure. Invariant transverse measure, which means that when I have, each time I have an arc which is transverse to the leaves, I have a measure, Lebesgue measure of full support on this arc. This is part of the definition of a measured foliation, and then this measured this measure here, this measure on this arc, is invariant when I push the arc along the leaves. And this means that if I have another arc here, another transverse arc, equipped with a measure of full support, etc., because it's part of the definition. And if the two arcs are obtained just by pushing the first arc onto the other by sending each point to a point such that it stays on the same leaf, then these maps are measure preserving. So an invariant measure is an invariant transverse measure of a foliation is a measure on transverse arc, which is invariant by this family of maps, which are called the holonomy map, or local holonomy maps. Okay, so now for an ideal triangle, this is its horocyclic foliation. There's a canonical transverse measure where each time I take a transverse arc like this, I say that the transverse measure, well, is the one induced by the Lebesgue measure. I mean the hyperbolic length element on the boundary of the triangle. So I push this arc here on an arc on the boundary. I push this arc here, and I say that the transverse measure of this arc is the same as the Lebesgue measure on this arc, and whether I push it here or here, it's the same thing, because the way we constructed this horocyclic foliation, these maps are length preserving or measure preserving. Okay, and it gives me, so this horocyclic foliation on this surface, the horocyclic foliation on this surface becomes itself equipped with a transverse measure. So this is a hyperbolic surface, horocyclic foliation is itself a transverse measure. So to do this, I have to deal with arcs which are not necessarily contained by necessarily contained in an ideal triangle, but in fact, to define a measure, if you define it on small arcs, then you have the measure on the whole transverse arc. Okay, so the ideal triangle leads us directly to this notion of measured foliation. Now I want to recall this notion of measured foliation, general notion of measured foliation on a surface. I need to say a few things about this. Because I want to define this first boundary. Okay, so now I have a topological surface. Well, let's say with some punctures. I don't draw them as cusps because this is a topological surface, so it has just a few punctures, and then I say that a measured foliation on S, well, it's first a foliation, except that since the surface is, since I'm drawing a surface with negative Euler characteristics, so I have to have singularities. With singularities of the following form. So I just draw the local picture like this, or like this, or like this, etc. So 3 prongs, 4 prongs, 5 prongs. Okay, so this is a foliation with singularities, and together with an invariant transverse measure, with an invariant transverse measure, exactly like we did before, so on transverse arcs. So you have to say something at these singular points. So the transverse arc, when these local holonomy maps arrive at a singular point, then there's a natural way to continue here to the left and to the right, and these maps here, from here to here and from here to here, must be measure preserving. Okay, this is the notion of invariant transverse measure. Since the measure is, as I said, a Lebesgue measure, we don't care about what happens at this point, in fact. Okay, this is notion of invariant transverse measure, and then I want to define or recall this, well, equivalence relation between two measured foliations. So this is generated by isotopy, so continuous deformation. If I deform continuously a measured foliation, I obtain an equivalent measured foliation. So isotopy, let's be more precise, preserving the transverse measure. So it's not just that the foliations themselves are isotopic or homotopic. It's also that there's an isotopy which preserves the transverse measure, which carries one to the other, and then the other operation is what is called Whitehead moves, and these are operations which involve connections between singularities. So I have a singularity here, a singularity here. This is my foliation, and the operation is not a local operation. It's a local, but in the neighborhood of a connection of a joining two singularities. So the operation sends this to this like this. So I have collapsed this arc joining two singularities to a point. This is the point, and this is also measure preserving. I want this to be measure preserving. Okay, and I did not change anything in the neighborhood of this egg. And then a little bit, more generally, I can have something like this, which goes to something like this. One is missing here, right? One of them is missing. Okay, so I have let's write here. So while the set of equivalence classes of measured foliations on S, this is denoted by MF. This is the usual terminology with script M and script F. This is the set of these equivalence classes. In fact, it has a topology. I will talk about its topology. You see, it's if S is a surface with genus G and P boundary components, MF equipped with its topology will be homeomorphic to some Euclidean space or vector space of dimension 6G minus 6 plus 2P. This reminds us of this homeomorphism between Teichmüller space and a space of vector space of dimension 6G minus 6 plus 2P. So there is a lot to say about this analogy here. These measured foliations, for me, in fact, there are a lot of structure on measured foliations, a lot of results which you can prove on measured foliations, decomposition, rigidity results, and so on, which are analogous to results which you can prove on Teichmüller space, but they are easier to prove in general. Here, I mean, on MF, as we will see, that you may use a lot of combinatorial techniques combinatorial techniques to obtain results which are analogous to results on Teichmüller space. For instance, here you have flows, something called the earthquake flow. You can define an earthquake flow on measured foliation space, which has analogous properties, which is a Hamiltonian flow for some symplectic structure here, and so on. I mean, there are several results like this. The only thing now that I want to say is that this is homeomorphic to the same vector space, and in fact there are natural homeomorphism here, natural homomorphism, and I will start now by describing one of these homeomorphisms because I will use it. Okay, so let me first erase here. Well, we can erase here. Let me describe this homeomorphism. Before this, maybe I should note the horocyclic foliation either of an ideal triangle or of a surface obtained by gluing ideal triangle is a measured foliation. We already said this, that it carries a transverse measure, but in this sense also, because you see the singular points here, I can create them by collapsing this region onto a tripod like this. And this is this operation here. The result is well defined. It's well defined. Well up to equivalence. This equivalence relation. The equivalence relation involves isotropy, so this is well defined up to isotropy. So I obtain a measured foliation. I obtain a measured foliation. The horocyclic foliations of a collection of ideal triangles. Forming a hyperbolic surface just by gluing them along their boundaries, give the horocyclic foliations give a well-defined something which I call horocyclic foliation, well associated to the hyperbolic structure. Obtained by gluing these ideal triangles. And then you may ask, so all these horocyclic foliations that I obtain in this in this way have all they all have singularities of the following type, that is tripod. So why do we care about the other types of singularities? These will appear, in fact, anyhow. These will appear, but the point here is that you see, when you have a surface S equipped with a decomposition into triangles, and a measured foliation transverse to the edges of the triangles, then there's only one possibility from the topological point of view in each triangle, and this is this one. This is this one, that you have only one singular point in each of these triangles. This is just by Euler characteristic, Euler Poincaré. It's Euler Poincaré index of vector fields and so on. I mean, I cannot have a foliation, a measured foliation. The transverse measure does not intervene here. I cannot have a foliation transverse to a triangulation where I have here singularities of this type, or two singularities, and so on. This is an easy topological lemma. Okay, so the result now is that I have a mapping which sends, as soon as I have a triangulation of a surface, I have a mapping which, if a horocyclic foliation in this sense. So if I have a surface obtained by gluing ideal triangles, I have a canonical measured foliation, canonical up to equivalence, and canonical element of MF of S. So I have remember that we want the surface to be complete, and this element in MF, so this is, let's give names. This is lambda ideal triangulation. This is my fixed ideal triangulation. Let's call the hyperbolic structure obtained by gluing these ideal triangulations, let's call it G. To G, well, let's call it I hesitate between Fg of lambda or F lambda of G. Let's call it F lambda of G. F lambda of G, and remember that this F lambda of G is a special measured foliation, class of measured foliation. It has the property that neighborhoods neighborhoods of punctures. Neighborhood of punctures are all annuli foliated by parallel circles. Okay, and this now leads us to a little bit of a modification of this, the definition of this space. I want to modify it a little bit. So MF as I defined it, the space MF, equivalence class of measured foliations, does not have this. I mean, does not involve this property. There's a space called, well, compactly supported measured foliations, and this is usually called MF, well, compactly supported of S. Usually I don't need S, I don't want to put S, but the C is important, and this is exactly the so these are foliations. So these are, well, equivalence classes of measured foliation on my surface S, which may have punctures. Well, with the above property. This is the property here. The property that the neighborhood of punctures are all annuli foliated by circles. And in fact, there's a map from Teichmüller space, the Teichmüller space of my surface S, into this space, MF compactly supported, but I will remove the C because all of them will be compactly, all of the measured foliations I will consider are compactly supported. And this map sends each hyperbolic structure to its horocyclic foliation. We called it F lambda of G. So lambda is fixed. Lambda is fixed, some ideal triangulation of the surface. And this is map, let's say this is a proposition. This map is well, I want to say that it's a homeomorphism, but I didn't define I didn't tell you how the topologies. So this is, let's say this is a bijection. And I will show now in a few minutes that it is a homeomorphism. The statement here, I mean, this involves the statement for each measured foliation that I can put for each measured foliation on the surface S, having this property there, I can find a hyperbolic structure such that I can find one hyperbolic structure such that this measured foliation is its horocyclic foliation. This measured foliation depends on lambda. This measured foliation depends on the choice of lambda.
Lambda is the ideal triangulation.
Yes.
The size of the triangle should be geodesics, right? So
yes.
But how we can define such a map? How we can fix lambda if the notion of geodesics depends on?
Okay, you are right. So this is a map. This is a map now. So given lambda on S, this map is from Teichmüller space to MF. So I'm rendering lambda geodesic. I'm making it geodesic before defining this map. And this is a good question because the question is, yeah, right? You understand? The question is, how can you make lambda geodesic? And this is another question which I don't want to discuss. I mean, I could discuss it now, but this I suppose that we know. Let's assume that we know that. Fix
is the topological type of curves and make them geodesic each time.
Exact. We make them geodesic each time. We straighten them out. Yes. This is exactly of the same kind of question and response, and the proof that simple closed curves which are not homotopic to a point, I can make them geodesic. And since you are asking this question, let me say why I raised it, but why this is called compactly supported. This is because you see, each leaf of this foliation, I can make it geodesic by the same argument that we just mentioned. I can, except if the leaves are homotopic to the except for these leaves which are homotopic to the puncture or to the cusp. So in order to have something which is where each leaf is geodesic, because at some point I will need this, I will replace the measured foliation here by something more geometric where each leaf is a geodesic. I should remove all these. I have to remove all the closed curves homotopic to cusps, and the thing which remains is compactly supported. This is why these are called compactly supported. Okay, so where are we now? Yeah, so I want to say that this map is a homeomorphism, and I want to recall something about the topologies of these two spaces. You see, if remember that if we consider the simple case, the very simple case where my surface is just the union of two ideal triangles glued along one side. So we have these horocyclic foliations, 1 and 2, and then we said that, well, the Teichmüller space of this quadrilateral is parametrized by this shift parameter here. And I can use this shift parameter just to define the topology of this space. My question is to define the topology of this space. So here I can use this shift parameter. And you can imagine that when I glue several triangles, and when I glue them together to define like here and here, to define a more interesting surface, like here I would get a torus with one cusp. Then I would get other shift parameters and so on, shift parameters. And the collection of these shift parameters will give me a topology. In fact, it will give me a nice topology. Topology which, so for the resulting surface, the topology will depend on the choice of lambda, but then I have to do something and say that it does not depend. The different choices of lambda will give me, in an evident way, the same topology. Now let's look at foliations. So I have two, well, abstract, I don't want to see them as geodesic triangles. I have two triangles, and then equipped with let's make it. This is my singular point. This goes here. This goes here. This goes here. This is now the combinatorial version. This is just a measured foliation. This is just a measured foliation. I also have shift parameter here, because as we said, in each triangle there is exactly one singular point. I can measure the distance between these prongs when they arrive to this common edge, and then I can make also the gluing, and then I have all the other shifts, and then I have so I have also, the result is that I have also shift parameters. So if I use shift parameters associated to lambda here and shift parameters associated to lambda here, then this map is the identity map. This map is the identity map on at the level of shift parameters. So it will be. I mean, it's clear that it is a homeomorphism. But I don't want to do this, because then I have to deal with several things, and most of all. The results, all the results which I'm saying here, are valid in a much more general case, where the ideal triangulation, or the triangulation, is not necessarily a triangulation is not necessarily a finite triangulation joining punctures, but it could be a more complicated triangulation, what is called a lamination or a geodesic lamination. These shift parameters are not. These shift parameters are not as easy to manipulate as here. So I want just to recall the usual topologies, and in any case I will need it. I will need these two topologies. So I want to recall the usual topologies on Teichmüller space and measured foliation space. I will do this. Okay, so let's start with Teichmüller space, and let's recall that we have S, the set of homotopy classes of simple closed curve, which are essential, meaning not homotopic to a point and not homotopic to a puncture. And then I have a map from Teichmüller space to all these functions, positive real valued functions on S, which to hyperbolic structure G sends, which to hyperbolic structure G associates the map. Let's call it gamma, the length of the geodesic, or this length of the shortest curve in the homotopy class gamma. Okay. The statement here is that this map is injective. This is not very difficult to see. This is not very difficult to see. You see what I'm saying here is that the collection of lengths of simple closed curves parameterizes Teichmüller space, and this is just, you see, this is proved. This can be proved by decomposing the surface into pairs of pants, into geodesic pair of pants. So as soon as I have a hyperbolic metric, this is for surfaces of finite type. For surfaces of infinite type, there are complications. But for surfaces of finite type, there is a standard way of decomposing the surface into here it's two pairs of pants, geodesic pairs of pants, and then we saw last week, in fact, that the boundary lengths, the three boundary lengths of the geodesic pair of pants determine the isometry type of the pair of pants. You remember this? In fact, we said this in a slightly different manner. You see, we have the proof is, the usual proof is that you take the geodesics, you take the length minimizing arcs between boundary components, and they decompose the geodesic pair of pants into two right-angled hexagons. These right-angled hexagons share three arcs in common, so both of them are so they are isometric to each other. This is something we said last week using a trigonometric formula. In fact, this side is also equal to this side. This implies that this side is also equal to this side, and so on for the three other sides, which makes the two ideal, not ideal, the two right-angled hexagons. I will come to ideal later on. Right-angled hexagons isometric to each other, and they are determined by these three lengths here. So the pair of pants is determined by its three boundary lengths. If the surface has cusps, then I have to deal with pair of pants in pair of pants in the pair of pants which have some cusps, and then the same thing I have to deal with hexagons. I have to deal with hexagons, but degenerate hexagons where one of the sides or two of the sides or three of the sides are zero, and I have the same result, the same thing, exactly the same thing. So I come here to the fact that all the three boundary components determine the isometry type, but then when I glue the pair of pants, I have three more parameters, which are these shift parameters, right? These shift parameters. They are determined by, and this involves a little bit of hyperbolic trigonometry. They are determined by the lengths of so each shift parameter here, each shift or twist parameter is determined by exactly the lengths of two transverse curves two curves which cut transversely and with minimal intersection this curves of the pair of bands. The length of so you see when I translate here, when I do a small shift, it's the length of these two curves which will change. So I'm not going to do this, but this is the way to prove that this map is injective. That the length of the simple closed curve, the collection of lengths of the simple closed curve determines the hyperbolic structure. So again, because it determines the hyperbolic structure in each pair of bands by this easy argument, and then by a more complicated argument, it determines also the shift parameter. The shift parameter. This is classical first-order theory. So this is this map. This is this map here. This is this map. This one here, which sends Teichmüller space into this space of functions. So I have an analogous map. Which sends MF. I can put compactly supported if I'm considering surfaces with punctures into this space also by sending a measured foliation to this function here, where gamma is sent to the intersection number of f with gamma, and this intersection number means the minimum transverse measure with respect to f, with respect to the transverse measure of f of an arc, of a simple closed curve in the homotopy class gamma. So it's the same thing. Instead of taking the minimum of the length when I have a hyperbolic structure, here when I have a measured foliation, I take the minimum intersection function. As I told you before, there's a complete parallel between these two theories of hyperbolic structures and measured foliations. And for hyperbolic structures, the curve which realizes the minimum is unique. This is a unique geodesic in the homotopy class. In the case of measured foliation, it's also a unique curve up to two closed curves which up to this relation, two closed curves which realize this minimum bound a cylinder. They bound a cylinder. They bound a cylinder with closed leaf. This is a nice combinatorial result, which I will not talk about now. But so there's a kind of uniqueness here for the curves which realize this minimum. Kind of uniqueness up to something which is not difficult to write if you are interested. Okay. Now the next result, you see, before the result, Teichmüller space and MF compactly supported, if you want, are equipped with the induced topologies from these injections. Here I put the product topology. The product topology. They all, both of them, they arrive in the same place, in the same space, in the space induced topology from product topology of this space R plus to the S. And then this is also, so this is a definition, this is a proposition. The two images, this image, the image of this space, the image of Teichmüller space here, and the image of MF here, the two images are disjoint. This is not difficult to see. This is not difficult to see. The reason is that when you have a hyperbolic surface, hyperbolic structure on a surface, the length of closed geodesics is bounded from below. You have a shortest geodesic. You cannot have a sequence of geodesics whose length goes to 0. Whereas if you have a measured foliation, in fact, and you consider these intersection functions, then the length, the length may be 0, because you could have the measured foliation may have a closed leaf. So, and the minimum of intersection of the measured foliation with this closed leaf is 0, which is something which you cannot have there. The length of a closed geodesic cannot be 0. So intersection, and if the foliation does not have a closed leaf, then by a structure theorem, which I talked to you about sometime, you have leaves which come. You have leaves with leaves which are recurrent. Leaves in which you have leaves where at each point you start at each point you start in one direction, so you will the leaf will be dense in its support. The leaf will be dense in a subsurface. So the leaf will come back here. What I want to retain is that the leaf will come back closer and closer to where it started. So and this implies that a sequence. No, not this one. There's a sequence. Well, there's a sequence. So this is the sequence here. I arrive, I said, closer to my point, and then I make it transverse. I can make it transverse to the foliation. And where if I arrive even closer, so the total transverse measure of this curve, which I mean we can prove it's non-zero, non-homotopic to a point, is smaller and smaller. So there's a sequence of simple closed curves. Let's call them gamma n, such that I of f and gamma n goes to 0 when n goes to infinity. There's always such a curve. Either there's a curve whose length is 0, and in this case this is trivially true, or if there's no closed leaf on the foliation, then I can find such a sequence as I said now, because of this recurrence. And so this is a phenomenon which does not occur there. So this shows that the images are disjoint. Okay. This shows that the images are disjoint. Now there's another proposition, and then we'll make a short break after this other proposition. The other proposition is also, it has two parts, in fact. One part is that, okay, you see, I want to consider, instead of this space R plus to the S, I want to consider its projective space. So the projective space of all functions, this space of all functions, I can make the positive reals acts on this space of all positive real functions, and I get something which I call the projective space. And the statement here is that T, in fact, not only injects in this space, but it injects this natural injection there, induce a natural injection into the projective space. This is part of the okay, so the thing I'm saying here is that I cannot have two hyperbolic structures on the same surface which have whose length function here, whose length spectrum is a multiple of each other. Okay, so there are several ways to see this, but if you want, you can say, okay, if I have I'm cheating a little bit, but if I have, suppose I have a hyperbolic structure G, if I have another hyperbolic structure G prime where the length spectrum is k times the length of G, then, well, whatever the lengths are, all these lengths of simple closed curves, all these lengths of when I decompose into ideal triangles and so on, everything becomes homothetic, and this is not possible. I mean, unless unless G prime is a multiple of the metric G, which makes the curvature of G prime not constant equal to -1, but another constant. Okay, so this is this proposition. It needs a proof, but this is classical. This is very classical. The second thing is a triviality. The second thing is a triviality is that, well, the projective space PMF, instead of this map here from PMF into this space, I would take the projective space, because measured foliations, I can also make the positive reals acts on measured foliations by multiplying the transverse measure to by a constant. PMF, well, this is injects in this projective space, and the two images are disjoint. This is as before, exactly for the same reason as before. The two images are disjoint, and now this well, it's not this is a theorem. This is a theorem. This is the basic theorem for first-instance compactification, is that the image of PMF, in fact, is the closure in this projective space of the image of Teichmüller space. Remember that here we are talking about compactly supported. We're talking about compactly supported, but I don't want to insist on this. Okay, this is one thing. The second thing is that while the images are disjoint. The image is disjoint. This image is the closure of this one. When the image of Teichmüller space is homeomorphic to a ball of dimension 6g minus 6, and the image so PMF, I want to say PMF. You see, I told you a few minutes ago that the MF itself is also homeomorphic to R to the 6g minus 6, but this is if I include the empty foliation, the zero foliation. But in fact, if I don't include the zero foliation, it's homeomorphic to R 6g minus 6 punctured, and this is why I have this statement that the image of PMF in fact is. This is something you have to prove. I mean, this is something which is not trivial. This is maybe the main non-trivial theorem which I said now. This is a theorem of Thurston. The image of PMF is a sphere S of dimension, well, 6 of dimension 6g minus 7. And the union in fact is a closed ball B of dimension 6g minus 6. This is also something you have to prove. It doesn't follow from the two preceding things, because you can glue a sphere to a ball and the result is not a closed ball, but this is also and this is Thurston's compactification of Teichmüller space, and this is what I will use now for the for my discussion of the limits of stretch lines. So we stop for 5 minutes.
Is there any relation between this embedding into R in the power of Z and the map F lambda?
Yeah, it's a good question. No, a priori no. A priori no. It's a good question. In fact, you can. I mean, probably you can do again this compactification using F lambda instead of this map. Let me mention that the map F lambda is valid in a much more general case than something which I already said, than the case of a triangulation, of a discrete triangulation. It's associated with something which is called lamination, and there are much more results which you can obtain, and much more structure which you can obtain when you use laminations instead of triangulations. You see, the only thing you need is to decompose your surface into ideal triangles. The decomposition into ideal triangles is not necessarily obtained by using a triangulation of the surface. Let me just state. I don't want to go into the details, but you can take an arbitrary measured foliation. You start measured foliation on the surface. You replace. You see. You look at the foliation, measured foliation induced on the universal cover. You have to first. You have to know a little bit of hyperbolic geometry. You have to prove that each leaf here, when you follow your leaf on the surface and so on, has two endpoints on the boundary. This is the first proposition, and then what you do is that you replace each leaf by you replace each leaf up there by the geodesic, joining these 2 points. You do this equivalently. You come back to the surface. You get something. You get something on the surface which is not a foliation but a lamination, geodesic lamination. Geodesic lamination. So this geodesic lamination this is on a closed surface. I mean, it could be on an open surface, but let's do it on a closed surface. This geodesic lamination is a collection of geodesics. In the upper in the upper image there, in the hyperbolic plane, the left is something which looks like this. In fact, collection of geodesics. Either all the complementary components are ideal triangles. In this case, you have a decomposition of the surface into ideal triangles, and this is what I said is something which is more general than an ideal triangulation, because these leaves are I mean, they are going in the surface. I mean, they can come back and make they may be closed leaves or non-closed leaves and so on. They may be transversely in general. They make a Cantor set. You see, that's a nice dynamics of these leaves. Anyway, so if it's not decomposition by ideal triangles, well, then you can add finitely many leaves here, which will decompose each complementary component into ideal triangles. So these leaves will spiral along the components of your lamination. In the same way as we said that you could have a decomposition of the surface by closed geodesics, and then you can add leaves which spiral along these closed geodesics here, the boundaries of the pair of plants, and decompose each pair of plants into ideal triangles. And when you have a general lamination on a surface, you can also add finitely many leaves on the surface that decomposes it into ideal triangles. This is a whole theory. I'm not going to do it now, but this is what we mean by. In fact, I will use this. This is what we mean by a general lamination. And when you add these spirals, if your initial lamination you started with is a geodesic lamination, then the new lamination is no more a geodesic lamination, but it's okay. It decomposes your surface into ideal triangles. In each ideal triangles you have these horocyclic foliations and so on, and then you have this homeomorphism. Now the homeomorphism will be between. Now this is lambda. Lambda is my generalized triangulation or my lamination, and then there will be a homeomorphism between the space of compactly supported or not measured laminations which are transverse to lambda and Teichmüller space. And this condition of being transverse to lambda is not automatic anymore. Is not automatic anymore as it was in the case of an ideal triangulation where all the leaves goes to the cusp, because in this case any closed curve or any geodesic lamination here is compactly supported. This is where the compactly supported is important. Compactly supported is transverse to this to this triangulation. Whereas in the general case, it's not correct. Okay, so let me now talk a little bit about the compactification, and I have a lemma which I want to, which is important lemma. It's an important lemma in this theory of Thurston's compactification. The lemma tells you the following. We know how to define this compactification. We already defined it. Let Gn be a sequence in Teichmüller space, say, a sequence which goes to infinity, that is, which for n large enough, it's outside any compact set. If I take a compact set, then for any n for n large enough, it will be outside the compact set. This is what meaning. Then, well, Gn converges to F, and this is the projective class of a measured foliation F. We said that the elements on the boundary of Teichmüller space are projective classes of measured foliations. So this Gn converges to such an object if and only if there exists a sequence Xn positive reals. This is almost from the definition such that, well, Xn Gn converge to F. Let's say there exists Xn, and here, if and only if there exists a representative F of this projective class F, okay, if and only if they exist, and they exist such that this converges to F, in the sense, well, in the usual sense. I'm just recalling here the definition of these spaces, the embeddings and the convergence in the space. For any gamma in S, then we have Xn Lgn of gamma converge to the intersection function of F with gamma. And there's an important thing here. Which is almost trivial, but I want to just mention it. This sequence S. This is just from the definitions, and then in fact the sequence Xn necessarily goes to 0. The sequence Xn converges to 0 because when this hyperbolic structure, this sequence of hyperbolic structures is going to infinity, then there are necessarily curves which are becoming longer and longer, and I need this. This implies that the topology of Teichmüller space is defined by a finite number of curves, and then these, if I look at only these, then some of them will go to infinity, and this implies that this sequence Xn goes to 0, and this is very important. I mean, if you think a little bit, if you want to understand how this compactification occurs, then you will see why this Xn goes to 0. It uses everything I said. I didn't explain really how you glue Teichmüller space to its boundary, But I gave the hints, and I think if you want, we can talk about this, or you can read this. This is Thurston's result. Okay, so now I want to prove this result now, which is not in Thurston. This is the result. I said I want to say something about limits. Limits of stretched lines. So if okay. So let me recall something we did last week. So to a hyperbolic structure, or even I recall this today. To a hyperbolic structure, we have lambda. Lambda, say ideal triangulation, but it could be a more general geodesic declination. G gives F. We call this F lambda of G. This is the horocyclic foliation, and we said that this is a bijection. But what I'm saying now that we understand the topology is that this is a homeomorphism. And then there's an action of R plus, the strictly positive numbers now. Before it was the non-negative numbers, and now it's strictly positive number. Now this acts on MF, or MF compactly supported. This is from T to MF compactly supported. There's a natural action. And as we said, this natural action, these are the orbits are Thurston's stretch lines. They are geodesic for this. They are geodesic for his metric. They are geodesic for his metric, for Thurston's metric. They are not the unique geodesics, but these are important class of this is an important class of geodesics. This is a distinguished class of geodesics, and the statement now, which does not follow from everything we said. The statement is that this is a general statement. This is that the any stretch line, such as this one, say, I didn't give it any, I don't want to introduce more notation. Any stretch line like this one, you see the stretch line consists in, the stretch line is a line in Teichmüller space. It's a line in Teichmüller space which is obtained by multiplying the horocyclic foliation by some constant and then taking back the corresponding hyperbolic structure. This is how I get lines in Teichmüller space. When I say the orbits are Thurston stretch lines, this means the orbits in here. The orbits in here, and not the orbits in measured foliation space, right? Okay. So any stretch line converge to to the point. If I use this notation here, corresponding to the converge to the point, F lambda of G in BMF in Thurston's boundary. This is what I want to This is what I want to prove now. This is what I want to prove. And the proof is some hyperbolic geometry in ideal triangles. The proof is based on the following lemma. In fact, there's a lemma which I want to write, which I called. So this is in an old paper of mine. I told you this reference. It's in Mathematische, 1987. This is the first paper I wrote on this subject. And this is a lemma I call the fundamental lemma. Okay, so how did I formulate this? Yeah, let me copy it from here so that I don't make mistakes in the notation. The fundamental lemma is that, okay, for any homotopy class of simple closed curves S, we have, it's by purpose that I put here for any and then another for any here, for any G in Teichmüller space. Then again, we have what? We have a double inequality. I of f lambda of G and gamma is less than LG of gamma is less than I f lambda of G and gamma f lambda of G and gamma plus a constant here which is 4 times I of gamma and lambda. Did I make a mistake here? Yeah, this is correct. This quantity here does not depend on G. This is the important thing. This quantity here does not depend on G, and this is why I have put here for any G I have put it. It stands alone here, and so. So let me tell you how. When you have this, so this lemma gives easily this result here using the criterion I gave. Using the criterion I gave for convergence in Teichmüller space, the criterion which does not depend at all on the choice of ideal triangulation or anything like that. And I just want to tell you the method of proof of this lemma here. So there are two inequalities. I will tell you how you prove the first one. So the important thing is that we are comparing lengths with intersection number. So we are comparing lengths with intersection number, and for the result which is there, we want to compare. So length with intersection number with the horocyclic foliation. And this is the thing which is telling me now that this horocyclic foliation contains the information about the hyperbolic structure and allows me to prove these theorems about the behavior at infinity. And so once you know what you want to do, then the proof is rather easy. It's easy in the case of a discrete, well, of a lambda which is a lambda which is an ideal, well, a lambda which is a discrete triangulation like this, an ideal triangulation, the proof is much, well, it's more difficult. More difficult in the case where lambda is a lamination, as I explained. And then after this paper, there were several papers. You see, this is, I think, 1991, where I consider the case of a general lamination and so on. And then there were other papers. I gave you last week. I gave you some references on behavior of stretched lines and backward stretched lines, and this is again more complicated. So this is now a little bit technical, but what I want to show is this: how you compare length of geodesics with intersection functions with the horocyclic foliation. And this is just, in fact, at the end it becomes just, the proof becomes just a picture. So I take, so now I work with a special ideal triangle, which is this one. An ideal triangle where in the upper half plane, the one vertex is at infinity. And here, here I have 0 and 1. Okay, and to prove the first, so here I have the rest of the surface. Here too I have the rest of the surface. This is just one ideal triangle in my surface. So I take my curve gamma. And I make it geodesic. Make gamma geodesic. So I want to prove the first inequality. When I will, I will not prove the second inequality because now we will have to go for lunch after this. But the proof is almost the same. But instead of making gamma geodesic here, I will make gamma having minimal intersection number with the foliation. And then doing an equivalent thing, replacing foliation by hyperbolic structure and vice versa, I will prove the second inequality. So now let's do the first inequality. So make gamma geodesic. So this is, well, okay, so there are, and I look at intersection of gamma, of this gamma, which is now considered as a geodesic. Take the geodesic in some atomic class. Well, with one foliated region. Let's say with one foliated region of an ideal triangle. Each ideal triangle has 3 foliated regions, 1, 2, and 3. And I look at this one, and I say that there are 3 cases. 3 cases depending on the intersection of gamma with the boundary of the triangle. So, for instance, this is gamma. It could be like this. Remember that these are horocycles. And this is a geodesic. So they are not necessarily transverse. I could have here a tangencies or whatever. So this is the first case. This intersection has 2 points in common. With the boundary of the triangle. So 1 and 2 points, or it may have second case 1 point in common. So it could be, so this is the boundary. This is not on the boundary of the triangle. It could be like this, or number 3, 0 point. So it could be like this. It does not it intersects this part of the triangle, this cusp, this foliated region of the triangle, but it does not intersect the boundary of the triangle. And now remember, there's a very simple lemma of hyperbolic geometry, saying that let's look at this. Let's look at this one. Let's look at this one, and let's look at this one, and let's make it transverse to the foliation. Transverse to the foliation. Transverse to the foliation. Now, if I make it transverse to the foliation, then the transverse measure here, by definition, the transverse measure is the hyperbolic length from here to here, right? And the lemma which I said, the easy lemma of hyperbolic geometry, is that the length here of this geodesic is greater than its projection on the boundary of the triangle. Okay, this is because the metric here is ds squared dx squared plus dy squared divided by y squared. Okay, okay. So the conclusion here. Yeah, let's do it here. The conclusion here. Let's introduce just a slight notation. A slight notation is this one. The intersection function with a big I, the intersection function of f lambda of g with gamma. So when I say this is traditional, when I write a big I, it means this intersection number is the minimum intersection number in the homotopy class. But when I write a big I, it's just this physical intersection. So this intersection now, which I see here, the intersection number with this foliation, which is not the minimal intersection number, but it is less. This intersection number here is less than, well, it's less than the length of this piece. Okay, because of this projection which is contracting. Now I do the same for this one. In fact, I make it. Maybe it was transverse, maybe it was not, but anyway, I want to make it transverse. I want to replace it by a transverse curve, and I have the same thing here. I have the same for this piece here. Instead, I have the second piece. Its intersection number is less than the length, and this piece here. Each time I have a piece here, I push it in the non-foliated region, and then its intersection number with the foliation becomes 0. Its intersection number becomes 0. The result. So the intersection number, in fact, the actual intersection number of all these pieces is always less than G gamma. Say this is gamma star, if you want. And now I'm talking about this gamma star. The pieces are gamma star. And then I add them all. I want to add them all. I add them all, and then I find that intersection number of FL of G, and now of gamma is always less than LG, NG, LG of this. This is gamma. Sorry, this is, well, gamma star. You see that there's a gamma star and a gamma here, non-star. This is a non-star here, and then I will take the sum. I'll take the sum, and I know that the minimal intersection number is less than this one, so I get G gamma here is less than LG of gamma. This is the first inequality. The second inequality is a little bit more complicated, but I will not do. But it's the same. So everything boils down to a comparison of lengths between and length and transverse measure in ideal triangles, and then I have. So in the case where lambda is more complicated than a discrete triangulation, this needs more work, and then the backward for the backward stretch lines, I need a little bit. A little bit more of notation. You see this, and I need to explain what is uniquely ergodic measured lamination, and so on. But I will stop here. So if you are interested, we can talk about this later. And that's all these papers. So this is one of the first results which I wanted to explain. Next time I will explain other results on this metric. You see, you have a metric. You have a metric on a space. You have a metric space. So you have all sorts of results which you ask. Is this, for instance, you can ask results about the isometries of this metric. You see, when you have metric spaces like this, which look like, they look a little bit like negatively curved. You can ask whether the isometries, there's a classification as the isometries of hyperbolic space, hyperbolic plane, or let's say hyperbolic plane dimension 2 into elliptic, parabolic, or hyperbolic. If the isometries of this space have invariant axes and things. Now that you know that you have these stretch lines which are geodesics, which go in the good cases from a point on the boundary to a point on the boundary. So you'll ask whether there are isometries of the space that preserve these stretched lines and so on. And there are a lot of results on this metric, Thurston metric, which I think are interesting. So next time I will explain another result.